I assume you say that I should go ahead, but I can still not hear you. Okay, so thanks a lot then for starting my invited talk here. So I will speak about spin excitation, anisotropy in the nematic state of DETWINNED iron selenide. Did I take a laser point? Okay, good. So let me begin with just summarizing or thanking all of my collaborators. So this is a project of my group at the Scherrer Institute in direct collaboration with the group of Jingye Liu at Beijing Normal University. And we collaborate also with Rice University in Houston, with the group on the theory side Shima Shi and with the experimental side on Tangent I. Let me begin with just reminding all of us how you now define nematic order in real momentum space, or in particular now the case of iron-based superconductors. On the left side, panel A, I show the typical magnetic configuration actually for the parent compound, the barium iron arsenide, where you have in the A direction a ferromagnetic coupling and in the B direction an antiferromagnetic coupling. So what you have there in essence is basically a breaking of the rotational symmetry. That means an inequivalence of the X and Y directions in the iron plane. So, and this is in principle now the definition of what it means as what it is in nematic order. So, but what does that mean now, for instance, for magnetic properties, the magnetic susceptibility? How would that look now across the brilliance zone? So, if you are now in the magnetic, now in the nematic phase, so basically below the nematic phase transition, you have a clear inequivalence also in momentum space. That means a clear inequivalence between Qx and Qy. You see like different intensity of the magnetic reflection peaks. So if you then look what is happening if you now cross the nematic phase transition, so when you are in a temperature regime above, is that you lose this inequivalence. You have like basically like this, again, equivalence of the magnetic response both in Qx and Qy momentum direction. So I just want to give you a little bit a background now on the iron selenide synthesis by itself and on the nematicity in iron selenide. So here on the left side, you can see the structure of iron selenide. So it consists of iron and selenium, where iron is in the oxidation state iron 2+. So the structural transition of iron selenide is at 90 K, and that's basically it's equivalent with the notion of nematic phase transition, which would then happen at 90 K. So iron selenide is a particular system because it has actually no long-range magnetic order. So the superconductor transition is very low, in principle 8 Kelvin only in bulk form, but it can be, of course, boosted in the thin film form and particular thin film forms of iron selenide on strontium titanate substrates. So basically, you can even achieve TCs of above 70 Kelvin. TC is highly tunable. So what is now the basic signatures with different probes on nematicity? So nematicity, what you have is basically as the first to signal now electronic nematicity is an anisotropy in the resistivity, like seen here. Basically, if you go below nematic phase transition, you have a different response of resistivity along A and B direction. So you have also an orthorhombic lattice distortion, exactly coinciding with this nematic phase transition, and you have a divergence of the nematic susceptibility, which you can see here. The nematic susceptibility will diverge when you approach the nematic phase transition. You see here the anomaly of the lattice distortion. Of course, going in line with that is also that your Fermi surfaces are heavily reacting on the nematic phase transition. So where you can see how the Fermi surfaces between the tetragonal phase, that means the temperature above the nematic phase transitions, are changing heavily when crossing to the nematic phase, basically crossing the orthorhombic phase transition. So basically, what is now the question is what is the origin of electronic nematicity? So it could be either orbital or spin-driven. Then, of course, then the natural question is also, what is now the correlation between the magnetic excitation, nematicity, and superconductor? So I just review very, very quickly what we know about low energy spin excitation, iron selenide. So the first thing which one was knowing is basically information spin excitation with NMR, where actually no anomaly was found the spin relaxation rate, which actually speaks then immediately for a rather orbital-driven nematicity scenario. Then, of course, inelastic neutron scattering was also done a lot on iron selenide, where you can nicely resolve the spin resonance mode. And basically, this spin resonance was seen to react heavily on superconducting transition temperature, as you see here. Basically, when you cross the superconducting transition temperature to low temperature, the S of Q and omega is just basically going up in an order parameter-like fashion. But what is now basically the connection to nematicity? If you plot here on the left side, shown left down, the orthorhombic lattice distortion and S of Q and omega obtained by inelastic neutron scattering, you see that you have a strong interplay between the spin resonance mode at 2.5 millielectron volt and the nematic phase transition, basically, which is basically looking both order parameter-like. That means actually this neutron study here and the comparison to the orthorhombic phase transition is actually that spin excitations could be actually directly connected to electronic nematicity, which again would speak for a spin-driven scenario. Then the inelastic neutron scattering community was studying even a DETWINNED iron selenide. They just show here the strategy how to do that. So the group of Pencheng Dai and also together with Jingyi Lu, they were developing a very smart method to DETWINNED iron selenide in an indirect way, because iron selenide, if you would just DETWINN it by pressing onto iron selenide crystal, you would really have trouble because it's very soft materials. You would really rather destroy it, or it would simply not be able to DETWINN it. But what these inelastic neutron scattering experts were developing is that you could indirectly DETWINN iron selenide just by gluing it on a barium iron arsenide substrate, and you can straightforwardly DETWINN barium iron arsenide, and just basically by now the lattice distortion, which is happening in the order of 0.36% in barium iron arsenide, then also passing the structural transition, you indirectly DETWINN also the iron selenide. So here you see actually how these neutron scattering groups were measuring the DETWINNing ratio with the help of monitor nuclear plug peak, and they could find out that they have a DETWINNing ratio of approximately 50%. So in their measurements, they were also showing immediately at low energy that the anisotropic spin resonance in the normal and superconductor state is really anisotropic. So both the spin resonance is anisotropic and in the superconducting state, shown blue here, between 1, 0 and 0, 1 direction, but also in the normal state. And then what is shown is that basically actually the anisotropy is kind of energy dependent. So it turns out the higher you go when you spin fluctuations, the basically stronger this spin excitation intensity anisotropy is getting, which is also shown here. So the authors of this inelastic neutron scattering study here, together with theory collaborators and also together with background information for very early STM studies, directly then putting forward that actually the superconducting parent is in this case spin fluctuation. So the open question now, which is basically the main thing which I'm tackling in this presentation here, is now what is now the evolution actually not on the low energy spin excitations, but high energy spin excitations across the nematic transition. And it's of course very difficult to study high energy spin excitations in inelastic neutron scattering. That's why we are resorting to resonant inelastic X-ray scattering, which I show you here, the setup which we have at the Swiss light source at the Scherrer Institute. You see this is like a 5-meter Rig spectrometer for reasonable high resolving power. So the resolving power our facility is like between 10,000 and 14,000. And I just explained very in a nutshell how resonant inelastic X-ray scattering is working. So it's a photon in, photon out spectroscopic probe of the electronic structure. You excite a co-electron into empty conduction band, and then now recombining the system is recombining the core hole from an occupied valence electron. You can create all kinds of different elementary excitations per solid, which are shown here. So you can study phonon, but excitations, also magnon excitation, orbital excitation, charge excitations. And the good thing is now that you can, very similar to inelastic neutron scattering, study both basically the energy of the low energy, medium energy excitations, but also the momentum transfer to the system. So it's really a nice complementary method to inelastic neutron scattering, and in particular very sensitive also to high energy spin excitation. So now I dive directly in to the study of detwinning iron selenide and doing the RIGS investigation on it. So you see the devices which we are using is exactly the same inspired devices as used previously with inelastic neutron scattering. So we glue our iron selenide onto barium iron arsenide, detwin the barium iron arsenide. By this we indirectly detwin iron selenide. And we have now made a RIGS comparison study between directly the barium iron arsenide and the iron selenide. So now is the question, what is the evolution of the high energy spin excitations with RIGS across the nematic transition? I'll show you what I show you first is basically how RIGS is basically probing the spin excitations in iron selenide. You see here to the left side the absorption spectra at the iron L3 edge. You see now here in red the absorption spectra, and you see actually the intensity of the spin excitations, which you can extract from this data, which is just following basically the absorption cross section. You make a RIGS map, you plot all the energy loss against the different possible incident energies across the absorption resonance. You see that actually you have a region around the absorption maximum where you see clearly some sharp low energy magnetic excitations, but the rest of the spectrum is really dominated by high energy fluorescence. What you see here in the middle is basically that you have a full dominance of high energy fluorescence, which is an incoherent process and which is not really a low energy excitation. And now the task for extracting these spin excitations is that you need to really make a decomposition between the electronic response in terms of fluorescence and in terms of the spectral function, which is expressed by an elastic line, or in most often cases just simply a Gaussian form of the resolution function. And when now doing this deconvolution, you can extract experimentally S of Q and omega S of Q and E, which you can fit then with the most common harmonic oscillator model in order to analyze this spin excitation mode. No, I'm getting stuck here. I'm back now. Okay, good. So I begin now with showing the experimental RIGS results by showing the reference measurement. For the reference measurement, we did RIGS on detwinned barium iron arsenide. Basically, we do that at the absorption resonance of iron L3, where we have the most cross-section for the high energy spin excitations. And by now detwinning the sample and by now varying the momentum transfer in the two directions, basically the 1, 0 and 0, 1 direction, you can clearly see that you have a clear high energy spin excitation anisotropy, which is exactly expected for a nematic material. Of course, you also have very dominant high energy spin excitations in diagonal direction and pi. So you see clear spin waves in detwinned iron-based superconductor or in detwinned barium iron arsenide. You can explain these high energy spinning excitations by a simple extended Heisenberg model, just shown here. Also, you can account for them by simple RPA plus U calculations. They're basically well understood. So now, how is the situation changing when you look at the iron selenide? So when we now detwin indirectly iron selenide by the trick of first detwinning by iron arsenide and then recording the spectra of iron selenide, you see also here a case that you have very clear anisotropic intensity behavior between the 1, 0 and 0, 1 direction. You have also intense high energy spin excitations in pi direction. So that means you have clearly anisotropic behaving spin excitations in detwin iron selenide. And if you now look at the energy scale of these spin excitations, which is around 200 millivolt, you realize that the energy scale is much higher than the dxz and dyz orbital splitting. So what we now see from this is that we have really a clear, unambiguous evidence of high energy nematic spin correlation. So basically, you can by RIGS now resolve the nematic transition or the spin part of a nematic transition really nicely by resolving the high energy spin excitation. So we were then studying these high energy spin excitations also as a function of temperature. What you see here on the right side, basically for barium iron arsenide, when you are heating up the system and you coming closer to structural nematic transition, you are getting basically much and more decreasing spin excitation anisotropy, and when crossing now the structural transition a little bit above it, you see that you basically totally kill the anisotropic spin excitation behavior. And the surprising thing is that the same is actually also happening here in iron selenide. You need to remember that you don't have long-range antiferromagnetic order. So also in this case, as you heat up the sample and you come closer and closer to the nematic transition, basically your spin excitation anisotropy is clearly vanishing. So that means the spin excitation anisotropy is decreasing the temperature and even disappearing when crossing the structure or nematic phase transition. Oops, I think I go in the wrong way. Huh? Yeah, okay, good. So as a last step, we were simply comparing our experimental results with different models, and what we compare here is a local moment-based picture description of the spin excitations of nematicity in iron selenide, and it is done basically in a really a local moment approach, and so a quadrupole antiferromagnetic moments which are describing this. And when you see here on the left side the calculations, when you compare them with the experiment, you see that this local moment-based approach is very nicely now accounting for the spin excitation anisotropy in iron selenide. The same, of course, for the pi direction. So what it means is that the calculated S of Q on a local moment-based picture, which is in this case antiferro quadrupole phase, is very well fitting the experimental data, which just here. And or which you see in combination or in comparison to on the right side, where from literature actually there is a paper of Kreisel here, and Anderson in the Frontiers of Physics, which were just coming kind of in parallel out with our data. And they were basically simulating the data when they were on archive, and they actually can very likewise basically account for our data, which means that basically that both local and itinerant theory approaches can capture our data. That actually speaks more for that this iron selenide system also is like iron pnictides is more to be seen as an intermediate coupling base and not a strong one. So I just slowly wrap up and summarize my study. So I've studied the spin excitation anisotropy with RIGS in DETWINNED iron selenide and compared it to barium iron arsenide. We see really clear, strong nematic spin correlations, not also only in barium iron arsenide, but also in iron selenide. The magnitude of the spin excitation anisotropy in iron selenide is more comparable to the barium iron arsenide. And you have, in both cases, actually a large energy scale of the high energy spin excitations. And in iron selenide, this energy scale is actually much higher than the energy scale of the dxz, dyz orbit splitting. And in addition, when we do the temperature dependent measurement, we see that the spin excitation anisotropy is actually disappearing above the structural or nematic transition. And all this taken together is for us a kind of indicator that the nematicity in iron selenide is primarily spin-driven, which is basically the main conclusion of our study. So I think I'm roughly done with my time, so I just thank you for your attention. I can still not hear you. Cannot hear anybody in the room. Try to crank up. No, I don't hear anybody. Very faint. You're very far away. I can't hear you. Maybe the other microphone, the hand microphone, actually was working. I realized the hand microphone, which does.
Okay, do you hear me now?
Yes, perfect. This is perfect.
Okay,
very
that's
clear.
right.
Thank you.
Do we have any questions to our speaker? Okay. Dr. Schmitt, we don't have any other questions. Thank you very much for your presentation again.
Yeah, this is a pity that you don't have questions, but I thank you a lot for sharing this.
Okay, thanks a lot.
Thanks a lot. Bye-bye.